Today we are going to be talking about chords and arcs, their theorems, and looking at a few examples that deal with chords and arcs. So the first theorem we have is that in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So basically what we're saying is that if AB, arc AB, is congruent to arc CD, then segment AB, which is that chord that it intercepts, is congruent to segment CD. And we can mark arcs the same way that we would mark chords. So we can say that that's congruent. Oops. We can say that this is congruent to this because these two are congruent. Okay? And the converse applies as well. So if I want to find the measure of CD, what I need to know, and I see it didn't come through, was that none of this, the arc measure kind of got moved. Okay. So on your notes, it should say arc CD. And in order to do that, we need to know that AB is congruent to CD. So let's add those markings. And if I'm going to find the measure of arc CD, it's going to be 108 degrees. Real simple. And like I said, the converse applies as well. Okay. Another theorem we have is if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord in the arc. So if I know that EG is perpendicular to FH, okay, then I know that FG is congruent to HG. Okay, I also know that the arcs are also bisected, so arc FK is congruent to arc HK. So if the measure of arc FK is 65 degrees and the radius of the circle is 5, we want to find GF and the measure of angle FEH. Now, because arc FK is cut off by a central angle, I know that this angle is 65 degrees. So now, in order to find the radius, or to find, GF, we're going to have to use trig. So we're going to, we know we're looking for FG. So that's opposite and hypotenuse. So the sine of 65 degrees equals opposite over hypotenuse. So x over 5. And we're going to multiply. So 5 times the sine of 65 degrees is x. So that length, x, is going to be, wrong way, approximately 4.53. Okay, so that would be our GF. I'm going to use approximately. The measure of GF is going to be 4 53/100ths. And then FEH, we're just going to actually double that because this is now going to be 65. So the measure of angle FEH is going to be 130 degrees. So we're going to use some trig for these problems. Right, so now in the same circle or in congruent circles, two chords are congruent if and only if they're equidistant from the center. So if I have my circle, and here's my center, I don't know why that little line comes up sometimes when I draw that. Okay, if I have a chord here, and if I have a chord here, the distance needs to be the same. And we're going with the perpendicular. We defined that several chapters ago. So if we know that these are equidistant, then we know that the chords, and if I name them A, B, D, and E, if I know those are congruent, AB is congruent to DE because these two chords or segments here, if I name that F and G, if those are congruent. Okay. So if I want to find the measure of XO and NO, we can do the converse. We have these chords congruent, so that means that these distances are congruent as well. So X plus 8 equals 4X plus 1. If I subtract X from both sides, I'm going to get 8 equals 3X plus 1. If I subtract 1, 7 is going to equal 3X. Okay. So what can I conclude from these diagrams? So we're just going to take a look, take a minute, write down everything you think you know based on these drawings, and then we can start the video up again and write it down. So in this case, first case, number 1, because we have AB congruent to CD, that means that arc AB is going to be congruent to arc CD. Okay. Now, because sometimes colored pencils help with this, I've got CB and AB the same measures. We can say that those are congruent. So AB is congruent to CD. And since that's true, we know that then AD, segment AD, is congruent to segment CD. Our last example, because we know that AB is perpendicular to CD, that implies that AD is congruent to DB. And it also, if I was going to put an E here, implies that arc AE is congruent to arc BE. So now we're going to use our theorems for some more examples. Okay. Because we're looking for X, and we know that this is here a right angle. Our radii are the same no matter where we go. So we can take this radius right here, and we can move that so that the hypotenuse of that triangle formed is 12. So then I can just use the Pythagorean theorem to solve that. So 3 squared plus x squared equals 12 squared. So 9 plus x squared equals 144. If I subtract 9 from each side, I'm going to get that x squared equals 139. And then if I take the square root of that, x is going to be approximately, so we'll use our little squiggly lines again, 11.79. Okay, so that's how we find x. Okay, we don't have an x on here. So let's find this side right here. Okay, again, this 12, we talked about in that class, is for that whole chord, and the 16 is for the radius. So we're going to change this to a 6 because that's half, this to an 8. So again, we can use the Pythagorean theorem. 6 squared plus x squared equals 8 squared. So 36 plus x squared equals 64. If I subtract x squared equals, I believe it's 25. No, it isn't. It's 28. All right. So x is going to equal the square root of 28. If I was going to leave that in simplest radical form, it would be 4 root 7. Okay, so make sure you read directions so you know how to leave your answers. So today we had 3 theorems that you can recap right here. In the same circle or congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord in the arc. And then in the same circle or in congruent circles, 2 chords are congruent if and only if they are equidistant from each other. So have a great evening, and I will see you in class.